in the program. I'm not from ETH Zurich. I'm from University of Lausanne. Well, it's not a big problem. I've been at ETH. I did my postdoc there a long time ago at Paul's place. I don't know if you remember. It was a long time ago. Okay, so the title of my talk is Generalized Additive Modeling of Hydrological Sample Extremes, and it's a joint work with Anthony Davison from EPFL and Marius Höfer from ETH Zurich. So we consider actually a hydrological time series at different stations in Switzerland. So the data have been provided by the Federal Office of for Environment in Bern. And so it consists on daily maximum flow over several years, okay, in terms of stream flow in the cubic meters per second. And so you see here the data at a station called Muota Ingerbol from 1923 to 2008. And so you see that it's all the data accumulated over a year for against the day of the year. So you see that if we fix a threshold high enough such that these points are considered to be extremes, exactly like what Paul did here, you can see that, well, we do not have IID data in no way. And of course we would have some seasonal pattern within day. Typically the flow would happen after snow accumulation or more melting due to melting of the snow, evapotranspiration, so it's more in spring. And also you can, if you zoom a bit, you would see that they might the extremes appear in clusters. So if you look at the same data, but this time over a year, so that is for every day, but over a year, and we fix the threshold high enough. So what you can look at is if you can maybe detect some long-term dependence compared to the short-term dependence we just saw before. And the lines here, the pointed lines, are they told us, well, there might be also that we find some discontinuities due to the change of the station, the location of the station, or that can be also a change of the instrument to measure the data. So that might also be a source of non-stationarity in terms of discontinuity. Okay, so this is the data we are looking at today. And so we saw that, that would be very current, presence of seasonality, trends, etc. So that is the traditional extreme value theory might not be helpful. The aim, again, is to look at the extremes to calculate a high quantile, like a return level. So the high quantile might happen beyond the range of the observation. So extreme value theory will be very helpful here, is the right theory to be used, but we have to adapt to the fact that the data are not stationary. So some variation due to, for instance, specification like altitude or change of the location of the station, orientation of the station, may be summarized parametrically. Other changes or other discontinuity or the non-stationarities might, like a long-term trend dependence, might be more non-parametrically modeled. So our aim, and this is what we are going to look at today, is to combine the point process explained here with this draw from Paul for the exceedances, so that is the extreme above some thresholds, with some smoothing methods to give a more flexible explanatory modeling of the high flow exceedances, and then a dynamic estimation of high quantiles like return levels. So the data are not declustered because we also want to model the short-term dependence. And then we will also look at a bootstrap confidence interval to assess the uncertainty of our model. Well, I'm not going to recall all this, the methods, the two EVT, the two main EVT methods. First, the traditional block maxima. It has been already shown before. So you know that if you take a sequence, then the max with suitable sequences A, Q, and BQ of normalizing constants, then you know that the limiting distribution must be a generalized extreme value distribution from which you can derive a likelihood and a log likelihood and then get estimation for the parameters of the GV. Okay, that's for the block maxima. With a lot of data like we have provided by hydrologists, we can deal with this because we have enough data to just look at annual block and then pick the yearly maxima and then maybe try to find if there are some trends. But it happens, especially in finance, we do not have so much data to deal with this method. So we normally look at the more flexible peaks over threshold methods, which is also explained here. So for which you decide for, you determine a high threshold enough, and the data above the threshold are your exceedances. And so the peak over threshold methods consider that the number of exceedances, NT, is approximately following an homogeneous Poisson process with a certain intensity lambda, okay? And independent to this number of exceedances above the threshold, the sizes of the exceedances are generalized Pareto distributed that I recall here. Okay, that works for the IID case, and even also for the slightly dependent case and stationary case in general. You have just to adapt for probably the uncertainty and standard error of your parameter estimation. And then you can also write down the likelihood for this peak over threshold model. Okay, so it's written there where a small j here is the density of the generalized Pareto distribution. But when you take the logarithm, then you see that it's split into two parts. One, considering the number of exceedances, so the Poisson process for the exceedant times, for the frequency of the appearance of the extremes, and the other part for the sizes of your exceedances. So that is the generalized Pareto distribution. So that means, which is here written, okay, it's a bit more complicated, but that means that inference can be done separately for the occurrence of extremes and for their sizes. So we took advantages of this also. So what we are going to propose is a dynamic EVT approach which uses a generalized additive modeling. So in the context of the EVT approach, it can be, that you consider theta, which is the vector of your EVT model. So it's either 3 for the GEV because it has 3 parameters, location, scale, and shape parameters, and also 3 for the peak over threshold representation because it has lambda, the shape psi, and the scale parameter beta. Okay, in the way that I wrote it just before. So if you tell this parameter, if you call it theta, then you consider this semi-parametric form for the parameters, for each of the R parameters. So that is the G here is a link function, so that can be, for instance, typically the exponential if you consider positive parameters or logit parameters if it's between -1 and 1. And so this part is purely parametric part, okay? You know you have a vector covariate, so that can be in our case, I know that, it can be, for instance, an indicator saying that from this date we changed the location of the station, so are we going to detect a discontinuity? Or it can be that you are dealing with several stations, so you parametrically inform with the covariates the altitude of the station, or something purely parametric. And the other, would be typically represent evolution through time. Okay, for instance, trend that can be over day of the year. Okay, typically like we saw before, and also that can be long-term dependence, so over year. Okay, so this is what we would like to model, that we want to allow the GPD parameters or the GV parameters to depend on some covariates in a semi-parametric way. So that is a part which is fully parametric and the other part is non-parametric. So for this, we also need to penalize our log likelihood in order not to have a wiggly an extrapolating estimation at the end. So we need some smoothing parameter to penalize the log likelihood. So this is the penalized term with the smoothing parameters here. The higher is the smoothing parameters, the smoother will be your solution. Okay, so this penalized likelihood is part of the likelihood then, and so we do this either for the log likelihood for the block maxima or for the Picova threshold method. And we are going to look at these methods but for the Picova threshold methods. So first, for the number of exceedances, so that is for the occurrence of extremes, we just have to allow the rate of the Poisson process to depend on some covariates. Okay, this is completely standard generalized additive modeling where the family is the Poisson. Okay? There is only one parameter, and then you can use the GAM function that is, for instance, in R, and you would have a solution that is very standard. And then you can fit several models, compare them with, for instance, the likelihood ratio statistic for the parametric part, and otherwise for the non-parametric part, you would typically look at the equivalent degrees of freedom, which gives you the effective number of parameters used for a given smoothing parameter. So there is a link between the smoothing parameters and the degrees of freedom. And then to choose the best degrees of freedom, you would, for instance, typically use the Akaike criteria, which would be minus 2 times the likelihood plus 2 times the degrees of freedom. Well, we'll discuss this later. And so now it's becoming a bit more complicated because we have, for the generalized Pareto distribution, so that is related to this part of the likelihood, so we have 2 parameters, and that's not standard. So we have to do a generalized additive modeling, but for 2 parameters. Okay? So we actually realized that if we keep the standard parametrization of the generalized Pareto distribution, which is written here, when we apply our model, when we use our model, when we develop our algorithm to let these 2 parameters depend on some covariates in a semi-parametric way, we got problems of convergence in the backfitting algorithm that I'm going to explain very shortly later. Why? Because they are not orthogonal in the sense of the Fisher information matrix. So it's not a diagonal, and when you update one of the parameters, say psi, then the value of psi will enter the Fisher information matrix in the non-diagonal, okay, and that will also influence the next value of beta, because the Fisher information matrix is used as weight in your iterative weighted least squares algorithm. So that is at least at each Newton-Raphson step of your backfitting algorithm, if you know a bit about generalized additive modeling. I will get back to that shortly later. So in any case, we had to find orthogonal parametrization for the generalized Pareto distribution, which is, by the way, always feasible. There is a paper on by Cox and Reed on this. When you have two parameters, you can always find a reparametrization which is orthogonal. If, of course, you can have an analytic form for the second derivatives of the likelihood in terms of the parameters, of course. So we find out that this, we introduce this nu, okay, which is the logarithm of 1 plus psi times beta, and it is going to be orthogonal to psi. We could also find another parameters, let's say, that depends on psi and beta, which would have been orthogonal to beta, but we prefer this parametrization because psi is difficult to estimate. And this nu will have also an interpretation which is also related to the variability of the data. And psi we let it like this because it gives you information about the tail of the distribution. So it's very important to have a value for psi. Okay, so then we can rewrite the likelihood, the log likelihood in terms of the orthogonal parametrization. And then, so we are going to consider two models, well, there's models, very general models for the two parameters of the orthogonal parametrization of the generalized Pareto distribution. So that is, well, they depend on actually there might be an exponential here because we expect nu to be, no, nu is a logarithm. No, it's wrong. It's already a log. It's already written here. So that's the semi-parametric form for the two parameters of the generalized Pareto distribution. And then, if you write down the penalized log likelihood, then you will have these two penalization terms, and then two smoothing parameters, one for the model for psi and the other one for the model for nu. Okay, where here it gives some details about this part, which is just the log likelihood for the generalized Pareto distribution. Okay. So now, how does it work? We use a smoothing spline, okay, cubic spline, sorry, to have this functional, non-parametric functional form for h here, okay. So the penalization terms is in terms of the square of the second derivative, and then we use cubic spline to estimate this non-parametric part of the model. So this is just, well, I will not go into the details of the natural cubic spline. So it uses the nodes, which are the ordered distinct value among t, and then, okay, so you can write down the penalized log likelihood into these terms. And then, so, as I said, the algorithm will be a backfitting algorithm for estimating simultaneously first for psi and then for nu. Okay, I alternate Newton-Raphson steps between psi and nu, and because we have orthogonal parameters, it converges. And then from nu, of course, we can get back to beta and get estimation for beta. We'll see also how to get confidence intervals for the parameters. So we use some techniques based on the bootstrap. And then from this, we can estimate what is of interest, so that is the return level. So the return level, you know that it's the 1 over p year return level. It gives you the value that your flow will not will pass once every p years. Okay, so this is the equivalent to the value at risk in the financial world. Okay, so using the Pickett's threshold methods, there is an explicit form for the return level. So you can just replace your parameters by they estimate, even if they have some non-parametric form, so generalized additive modeling parametric form, and then you would get a dynamic return level. So just a short demonstration on how it works. So for simulated data, so the details are also in the package QRM, Quantitative Risk Management in R, also coded mainly by my colleague Marius Hofer from ETH. And so we consider data of two groups, A and B, so that will be the parametric part of the model. And then we consider also a covariate, which is the year, okay? And then okay, maybe it's better if I show you. So we consider some non-parametric or maybe some specific form for lambda, okay, which is for group A, different than for group B, and also for the two parameters of the generalized Pareto distribution, which would be for group A this form and a decreasing form for B. So we try something a bit complicated. And also for beta, we consider there's two forms. And then we generated data from these true parameters. We applied our method, which consider that the covariates here, X gives the group, A or B. And the non-parametric form here will be for T, which is in our case the year. Okay? And so we generate some data and applied our model, and then you see the results for lambda first. So, well, again, this is just a generalized additive modeling, and you can also draw. So the line is the true value of lambda. The points are the estimated value, and the dotted line are some 95% confidence intervals. For Xi, you can see that it works also quite well. Well, the estimates are sometimes below the bounds of the confidence intervals, but the confidence intervals contain the true value. Same for beta. Okay, so beta hat is calculated back from mu and Xi. And also from this, we can calculate what is normally of interest, a high quantile estimation. So that is, in that case, the value at risk at 99.9%. So it's very far in the tail of the distribution. And so you see that it contains the true value at risk. So the confidence interval contains the true value at risk estimation. So even with very complicated model, we can be happy that it works. Okay, now going back to the application of this hydrological station, Murata-Ingenbold. So here what I did is just to look at for lambda, a dependence on year and day of year. But of course here, because my aim was first to be very explorative, to detect some trend, short trend and long-term trend dependence, I increased the degrees of freedom, so I did not use formally test or comparison or whatever inference to find the best model. I just increased it to look at to get an explorative analysis. So this is what I obtained. Actually, for evolution through year, we see that for different day of year, because it was also in the model, so I had to fix some day of year. So you see that, for instance, in July, which is the red curve here, we got some increase here, starting around the 60s, say, and then it started to slowly decrease for this station. If you look at how it appears for the within year, so that is the day of year, we fixed 2 years and compared the trend or the seasonality of the frequency of extremes of within year. Okay, so here I fix very high degrees of freedom, but as I said, I need an automatic method to select the best degrees of freedom, or equivalently smoothing parameter. And for instance, for the GPD parameters, this is represented here. So this is, well, my model will take into account, I do not have a fully parametric form here, because I noticed that the discontinuity due to change of the station I showed at the beginning did not have a significant effect. So actually, I only have two non-parametric form, which is one for the day of the year, and the second one for the dependence on through time, through years. Okay, so the first column here deal with Xi and shows the AIC for Xi in terms of the day of year, and then here in terms of year, and that's for beta. So for nu, sorry. So at the end, just to make it short, this is the three selected models for the Pickever's threshold method. So for lambda, we got that it depends on the, so the logarithm of lambda is written as a non-parametric form on t, which is the year with 3 degrees of freedom, and on the day of year with 3 degrees of freedom. For Xi, we got this form, fully non-parametric form, also significantly depending on the year and significantly depending on the day of year, and also same for nu. And if you look at the confidence interval for Xi, for instance, so that is through year, you will see that Xi is, well, is a positive. The estimation is positive. It's between 0 and 0.05, so which is not very high. But the lower bound of the confidence interval is below 0, so it's not sure that we are dealing with short tail or well, which domain of attraction is it? Is it Gamble or Weigel, but or Frechet? Well, it's evaluating significantly through year. For nu, which is more a parameter that deal with the variability of the data, we got an increasing trend through year. Okay, and for lambda, we got also, like we saw before, an increasing trend in the 80s, and then it started decreasing. So we can assess also, well, we can check the goodness of fit of our model by using the residuals for the generalized Pareto distribution. If you look at the residuals of the generalized Pareto distribution, so that the observed residuals, so using the observed data and the estimated parameters, if the model is correct, they should be standard exponential, which is here we see that it's not so, well, it's reasonable fit. Of course, if you would not have considered this evolution through time, believe me, so if you would have considered a constant model through time, you would have obtained something like doing like this. So the seasonality structure is still existing and shown in the residuals. Okay, so when from this model we can go back to the calculation of the return levels shows here. Yeah. So you know your threshold, and then you replace your estimator by the values. So you got at the end an estimation for dynamic return level, which is shown here, the 20 years return level over years. So that has been chosen for one particular day of year, because it's also the return level also depend on the day of year. And then you can see that you have a slowly increasing dependence, well, over a year, for the evolution over a year for this return level, which is okay. The points here corresponds to the data observed for this specific day of year, which was in July. Okay, I think I finished a bit early. Thank you very much.
We Thank you very much, Valérie.
Some related
Are there
reference.
any questions or comments? Yes, please.
Yeah.
Are you trying the same approach but keeping the shape parameter constant to see what you get for the scale for the the orthogonalized scale parameter?
Then it works.
Yeah.
If I
So if you keep, because since you have this behavior that is going from let's say from negative till positive the shape, so it could be that if you keep the shape constant, then you get something. So maybe
okay, there are two things here. First, if you keep the shape parameter constant, it means that you have only one parameter to model with the generalized additive modeling. So you will not have only the scale. Well,
the density of the quantum.
yeah, that we put aside because it's another log likelihood. But if you do that, you will not have a problem of convergence because your xi is constant through the algorithm evolution. That's the first thing. Now, if I got this shape for xi, it's completely, and that's what it's useful to orthogonize, it's completely independent on the shape of mu. Because my matrix is, it's a diagonal matrix, so the value of one parameter does not influence the value of the other. And now if I got this trend, which you're right, normally we don't like to have a xi, a shape parameter that is evaluating through time, but using informal tests, because we can only do informal stuff when we deal with non-parametric modelization, it's significant. I mean, I tested, I used AIC, I used informal likelihood ratio statistic to compare embedded models, and it's significant, it's there. Yeah.
Any other question or comment, you please?
Yeah, we had an experience of doing, in a simpler case where we had a trend in a simple atmospheric models, tuning the parameters, and in fact, but we were using GEV, so it was a different approach. In that case, what we found is that it was extremely effective and advantages, even in terms of the Akaika information criterion, to put the time as covariate for sigma and mu, but not to touch the shape parameter. Otherwise, you would have an explosion of the algorithm.
And the problem with the GV is that you have three parameters.
Yes.
And I think I saw a reorthogonalization which is orthogonal. Reparametrization which is orthogonal. So that would be interesting. Interesting to.
Anyway, there was a difference between subtracting the trend of the average and instead putting the time as covariate of the extremes. The result was different.
Okay, that's interesting. This is also related to a question I used to have, is that people used to tell me from the beginning, well, it's the first time I show this data, but they would tell me, well, it's obvious that you have to consider a non-constant threshold. If I do that, yes, of course I can do that. I would, probably use a moving window and then choose a threshold such that it corresponds to the 10% highest value. That would actually correspond more to the R largest method, because each time I have R largest values. And so this is also something that we did with Anthony Davidson.
Depends what the constraint.
Exactly.
If the mass or the...
Exactly. Yeah.
Any further question or comments? If not, then please join me in thanking both Petra and Valérie for a wonderful talk. Thank you.
And you too.